Good afternoon. Welcome to the Kavli Prize Lecture. The Kavli Prize is awarded every 2 years to scientists who have made influential contributions to astrophysics, nanoscience, and neuroscience, developing our understanding of nature at the largest, smallest, and most complex scales. The prizes are awarded by the Norwegian Academy of Science and Letters, which hosts the IAU Office for Young Astronomers, the Norwegian Ministry of Education and Research, and the Kavli Foundation. And the prizes are presented by King Harald at a ceremony in Oslo in September. The Kavli Foundation has partnered with the IAU in many areas for many years, including a triennial Kavli IAU workshop on global coordination of ground and space astrophysics efforts, Communicating Astronomy with the Public Conference in 2021, a Kavli IAU public engagement training program, and a new series of Kavli IAU interdisciplinary symposia. Thus, the IAU is delighted to host the most recent Kavli Prize laureates for today's lecture. The 2022 Kavli Prize in Astrophysics has been awarded to Conny Aerts from KU Leuven, Belgium, Jørgen Christensen-Dalsgaard from Aarhus University, Denmark, and Roger Ulrich from the University of California at Los Angeles, USA, for the development of methods that allow precise study of the interiors of stars. With their breakthrough research, the 3 laureates have laid the foundations of the theory of solar and stellar structure and have revolutionized our understanding of the interiors of stars. Roger Ulrich developed a mathematical model tying oscillations on the sun's surface to characteristics of its interior. Conny Aerts, a leader in Asteroseismology, studied massive stars to identify pulsation modes, leading to improvements in stellar evolution theories. Jørgen Christensen-Dalsgaard studied low-mass cool stars and the sun. He determined the sun's sound speed profile and developed Helio and Asteroseismology, now applied to stars observed with Kepler tests and other missions. Jørgen is with us in person today with remote contributions from Conny and Roger. Please welcome them all.
Thank you very much. Sorry for this. Let's just get back to the beginning. So, thank you very much to the Kavli Foundation for this very great honor. We are extremely grateful to have been selected to represent the field of Helio and Asteroseismology. But I think it's important to say right from the outset that we see this not as a prize for the 3 individuals that we are, but really as a prize recognizing the importance to all of astrophysics of the whole field of Helio and Asteroseismology. We have been part of the development of the field, but there are many, many other people, as will be clear from this lecture, who have also contributed. Unfortunately, Conny and Roger could not be here for this lecture, so I'm going to represent the 3 of us. We'll hear from Conny and Roger in the talk, and the slides have been put together by us. So they are a little bit inhomogeneous, but I think they catch the story. So what are we trying to do? We're trying to understand stellar evolution, from which, of course, goes from the formation of stars all the way to the final stages. And we have good models of that, we hope. But of course, to trust the models, we need to test them observationally. And so we need to find a way to look into the stars to see how well the models match the observations that tell us something about the interior of stars. And this is where Asteroseismology comes to the rescue, just in the same way as geoseismology, observing oscillations on the Earth's surface, allows us to probe the interior of the Earth. So we have observations of stellar oscillations on the stellar surface, and we can use that to get some information about the internal properties of the stars. And at a simple level, this is in a sense quite straightforward, because we know very well how the oscillations of stellar bodies reflect the structure of the stellar interiors. At least for simple stars like the Sun, this is straightforward. And so once we have the data, we can then try to invert the data to get information about the internal properties. We have the time series of observations, and then from that we can get the oscillation frequencies, and each frequency corresponding to an eigenmode of the star is then a measure of properties of the stellar interior. So that is what we're trying to do. But in this lecture, what I want to do is to go back to the beginning and to see how this has developed over the past more than 50 years. So let's start with Roger Ulrich and a brief presentation that he has recorded before this meeting.
Hello, I'm very honored and pleased to be here this afternoon. I'm sorry that I have to be here by video only. I'm very grateful to Jørgen for agreeing to present these presentations for the three of us. I have not come from a background in the area that I'm presenting now. At the time, I had just finished my PhD with Louis Hennier at UC Berkeley on the topic of convection. I had just agreed to go to Caltech and work with John Bacall on the solar neutrino problem. And just before I left, I attended a presentation by Ed Fraser on his studies of the velocities on the solar surface using instruments at Kitt Peak. What he showed was that the convection cells that he was studying seemed to disrupt the ongoing oscillations that had been discovered a few years earlier by Leighton, Noyes, and Simon. So what I'm going to talk about is how I went from that curiosity of what was going on where the convection cells seemed to disrupt the oscillations, whereas the general view was that they were supposed to be generating them according to the Light-Hill mechanism of convection or turbulence generating sound. There had been a number of papers prior to that time that had discussed the theory of generation of sound by convection in the solar convection zone. It was known that the solar surface was convective, but I thought, well, I needed to take a look at it. I had a model of the sun, a solar envelope, which I'd been using for my convection studies, and I thought, well, I'll just use that to analyze how the motions of the 5-minute oscillations propagate through the solar surface. And that was basically how I got started. So I want to have a presentation, a PowerPoint presentation that has a few interesting things, and I'll let Jørgen take that file and click forward through it. I've got explanations and images that explain how things developed in the early years of the Helio seismology. So I'll stop at this point. Thank you.
So the first indication of oscillations on the Sun was actually, as mentioned here, in a magnetograph that was being automated and calibrated. And Bob Howard, who was working on that, noticed that the servo, the calibration servo, moved up and down with a 5-minute period. And that was just a curiosity, and he didn't really think much about it. It was interesting, but not something to pursue. But then, just a few years after that, Bob Leighton and Noyes and Simon developed a photographic method to measure the Doppler velocity of the solar surface. And they actually saw the 5-minute oscillation as an effect across the solar surface with no apparent structure to it. Here's an example of such a Doppler image, and this can be compared with modern Doppler images obtained from the SOHO satellite. It's something that I'll return to later. So given these first early data, people started to make more detailed observations of how the oscillations varied across the solar surface and in time. And that allowed Ed Frazier to make the first of these, as we call them, L-nu diagrams or K-omega diagrams, where the horizontal axis is the wave number or the wavelengths, and the vertical axis is the frequency or period of oscillation. And this showed some structure to the power. The contours are power of oscillation, not a very regular structure, and these were very short observations over a small area of the sun. But this motivated Roger to look into models of how these oscillations might behave in the solar interior. And he found that they could be described as standing waves in the outer layers of the sun, and computed, these are the lines, computed how the frequencies depended on the wave number for different radial orders of these modes. Of course, at this point, the observation didn't really match the data, and what was required there would be to get more and better observations. And Roger actually started a project with a graduate student, Ed Rhodes, to make more detailed observations. But before they finished these these observations and data analysis, they were, you would say now, scooped by the German Franz Deubner, who did essentially the same thing, observed for longer time and over bigger areas of the sun. And again, in this diagram of wave number versus frequency, showed concentrations of power that more or less looked like what Roger had predicted in these lines, but not quite. So the model wasn't right. And that then went on. Just to explain a little bit of how this works, what we are looking at here are sound waves penetrating into the sun, and they penetrate to very different depths depending on how their initial inclination when the wave starts from the surface. These are waves excited by the turbulence in the near-surface convection. And so the waves that Roger computed and Franz Deubner observed were waves that were trapped quite close to the solar surface. But we also see waves that penetrate more deeply with larger scale on the solar surface, including waves that go all the way to the center of the sun. So that was yet to come, but at least these data told something about the properties of the near-surface layers of the sun. And we can compare Deubner's observations with the more recent data observed with the Mdi Instrument on the SOHO spacecraft, which again I'm going to get back to. And again here you can see the mismatch between the observations and Roger's models. And the first indication of what the cause of that came actually with when Ed Rhodes finished his observations, showing more detail than Franz Deubner's in 1977. And what are shown here are two sets of lines with different depths of the solar convection zone. One corresponding to the model that Roger was using originally, where the convection zone contains only 0.3% of the solar mass. And the second model where the convection zone contains almost 1%. And you can clearly see the improvement in the agreement between the observations and the models. So we already here got an indication that the solar convection zone was deeper than what had been modeled up to this point. The second thing that they also found was that the waves are advected by solar rotation. And so the observed frequencies depend on the internal rotation of the sun. And from that, they could begin to see some indication of variations of rotation with depths from near the surface to slightly deeper layers. Of course, we're still talking about these very near-surface regions, but at least there's some indication of variation in solar rotation inside the sun. So these were the contributions by Roger, and now we move to let's say, more profound issues. A different set of observations, and this field has been very much observationally driven and really reflects the ingenuity of the people designing these instruments. And the key person in that regard is George Isaac from the University of Birmingham. And he also observed oscillations of the sun, but he observed the sun as a star. So his observations were not sensitive to the small-scale motions that Franz Deubner observed and Roger modeled. But again, he found power at frequencies. You probably can't read the scale here, but this is a frequency of 3 millihertz, or a period of around 5 minutes. And so you see in these 3 years of observation an enhancement of power around 5 minutes, and you also begin to see structure in the power. And if you have a good imagination, and as theoreticians Douglas Goff and I did, you can see a pattern of peaks with roughly uniform spacing. And that is exactly what you expect for these modes with very large structure penetrating all the way to the core of the sun. And this was dramatically confirmed by, very shortly after actually, in 1980, in the southern summer of 1979-1980, where Gregg, Fossa, and Pomerantz went to the South Pole, a few hundred meters from the actual South Pole, to observe solar oscillations, and were lucky enough to get 5 days of clear weather. And of course, in the South Pole, the sun doesn't set, so they got continuous data over 5 days, and that showed this very clear structure of sharply defined peaks of power in the region around a frequency of 3 millihertz, or periods around 5 minutes. And this is a characteristic pattern of acoustic modes we see in low-mass solar-like stars. So from more modern observations, it could be the sun, it could be a star, we have this pattern. And if we blow it up, we can see there's a separation between peaks, which is a measure of basically the mean density of the star. So a combination of the mass and the radius, and you can extract other data to give both the mass and the radius from these data. And then you see fine structure in the peaks. You may barely see them at this scale, but a small separation that is a measure of the structure of the core of the star. And remember that these are modes that penetrate all the way to the center of the star. And so the different properties of the modes in the very center of the star depends on basically on the amount of helium in the core, and therefore also on the age of the star, because with increasing age, more and more hydrogen is converted into helium. So we can learn about the properties of the core of the star, and in this case the sun, from these observations. And that was an extremely important possibility in around this area of 1980s, because some of you may remember that there was a crisis for solar modeling in these years. Observations had been made of the solar neutrinos that are produced by the nuclear reactions in the core of the sun. And the detected rate of neutrinos from the sun were lower by about a factor of 3 than what the models predicted. Well, initially by a factor of 10, but then the models were, of course, improved. But at that point, it was impossible with standard solar models to reproduce the observations of the neutrinos, and therefore, of course, people tried to make other models by subtle modifications of the structure of the core of the sun, and they were able to get the neutrino predictions to agree with the observations with changes to the models that would not be visible on the surface. But in the late 80s, around 1990, Yvonne Ellsworth analyzed these low-degree full disk observed as a star data to show that the models adjusted to match the neutrino data did not fit the helioseismic data. And this very clearly indicated that there was nothing wrong with the models. And that was confirmed by later observations. We'll get to that in a second. So the reason for the lack of the low observed rate of neutrinos had to be the properties of neutrinos. So we now know, and that was a result that obtained the Nobel Prize some years later, that what happens is that the neutrinos generated in the core of the sun are partly transformed into other types of neutrinos to which these early observations were not sensitive. We have observations now that show all the neutrinos, but so the problem has been solved in that sense. But these seismic results were the first indication that this had to be the case. So again, the next development came from observations by Tom Duval and Jack Harvey. And again, what is shown here are frequencies of the modes as a function of wave number, but now extending from fairly high wave number, the region where Franz Leubner observed, all the way down to the low wave numbers that we see in George Isaac's and Eric Fossard's observations. And what that meant was that now we have data on all the modes, from the modes that penetrate just quite shallowly into the sun, and the modes that penetrate to different depths all the way to the modes that penetrate all the way to the core. And that basically allows us to peel off the different layers of the sun and measure, and in this case the sound speed, these are acoustic modes so they depend on the sound speed, to measure the sound speed as a function of position in the sun. And Dr. Scoff developed a mathematical technique to do that directly allowed us to go from the observed frequencies to the sound speed. And here shown the first results of that. The dashed line shows a model of the sun, and the solid line shows the observations, the inversion of the observed data. The technique becomes a little bit questionable in the core, but what this showed here is that the model is fairly good. It agrees with the inferred solar sound speeds quite closely. But if you then look at the differences between the sun and the model, you see quite significant differences, especially below the convection zone. And we were able to show that these differences are likely due to the fact that the opacity used in the model calculation were not correct. And that has since been confirmed by more up-to-date opacity calculations. And so we now have better agreement. But all this showed, of course, the potential for doing helioseismology. And that motivated the establishment of new observing facilities. And these were really major efforts in the late 1980s, early 1990s. And I'm going to highlight here two different efforts. One by the US National Solar Observatory to set up a network of observing stations around the globe. And the goal here is to get continuous data, not interrupted by the day-night cycle. We need that to get the best possible data on the solar oscillations. And by having these 6 stations, and this was a project led by John Leibacher, we could ensure a very large coverage, maybe up to 80 or 90% of the observations over very long time scales. The second way to do that is to observe from space. And the collaboration between ESA and NASA resulted in the SOHO satellite launched in 1995. And the SOHO is actually still operating. It had a few hiccups on the way. And the most important instrument on SOHO was the Mdi instrument led by Phil Sciarra in Stanford, which observes with very high spatial resolution the oscillations and allowed us to produce, again, a L-nu diagram, a wave number frequency diagram, that showed very, very clearly a very large number of peaks going up to high radial order, starting here at the lowest order, which disappears at a low angular degree, a low wave number, and allowed us to obtain extremely accurate frequencies of oscillations. So these are the frequencies inferred from the diagram I showed before. they're shown, again, the frequency as a function of wave number. They're shown here with 1,000 sigma error bars. So we determine the frequencies of oscillations with a precision at the level of about 1 part in a million, which is far more accurate than we know the gravitational constant, and therefore far more accurate than we know the mass of the sun. And then we can start to compare that with the models. And at this level, the model looks pretty perfect. Nothing like the deviation that we saw in Roger's model compared with the early observations. But of course, with such very detailed data, we can go further, and we can use, and actually use techniques developed in geophysics to analyze the differences between the observed and the model frequencies to determine directly the sound speed difference between the model and the sun, and thereby see how the models should be improved. And the results obtained around fairly shortly after the launch of Soho and the start of Gong is shown here in the relative differences between the solar sound speed and a model sound speed. And what you see, first of all, that the differences are small. This less than 0.5% in the squared sound speed. And I remind you that the square sound speed is proportional to temperature. So this very clearly shows that there's nothing wrong with the core of the sun, and therefore, of course, the solar neutrino problem can't be a question of errors in the model. But also you see that, in a sense, the models are awful, because there are error bars on these points. You can't see them. And so the model deviates from the sun, structure of the sun, with very many standard deviations. And I should also say that since this model was computed, there have been improvements in our knowledge about the composition of the solar interior, which have increased these discrepancies by a factor of a few. So the models are really not that great, and we are still working very hard on trying to understand what is wrong with the models. One of the aspects could be problems with the opacity again at a much more subtle level than before, and therefore collaboration with people computing opacities is really very important. And the second thing we can do with these data is to measure the solar rotation, the rotation of the solar interior. So this is a cross-section of the sun, just a quarter of it, with the angular velocity indicated by colors, going from 450 nanohertz for the rotation frequency down to 300 nanohertz. And so what we see is a variation in rotation with latitude. On the surface we knew that already, but now we see that that extends through the solar interior down to the base of the convection zone. And then there's a fairly sharp transition to more or less uniform rotation in the solar interior. And that transition region is actually where we think the solar magnetic activity is generated. So this has been very important for studying the solar dynamo. And what we're now trying to do here is to push these inferences even deeper towards the solar center to see whether the sun has a rapidly rotating core or not. The indications are that the sun is rotating more or less uniformly in the interior. And one important consequence of that is that the solar ablateness corresponds to what we see on the surface. And that actually means that the test of general relativity from the motion of Mercury is satisfied. There's no contribution from additional solar ablateness that will screw up that agreement. Now, this is the sun. And as I said, the oscillations are created by the turbulent motion near the solar surface. And that, of course, means that any star with turbulent motion should have oscillations. That essentially includes all stars cooler than the sun. The problem is to detect it because the amplitudes are at most a few meters per second. So it took a while before we were able to see oscillations in other stars. And the first detection actually came from my group in Aarhus, a star called Eta Botis. It's a subgiant, a star somewhat more evolved than the sun. And again, here we have a power spectrum showing power as a function of frequency. The maximum power is at a lower frequency. This is a star that's bigger than the sun, so maximum power is at a frequency of about 0.9 millihertz, 900 microhertz. And again, you see this, with the eye of face at least, the structure of sharp peaks. And so we were able to analyze the frequencies of this star, determine the overall properties of the star in that way, which matched the Hipparcos data that came out at exactly more or less the same time, but also showed that these frequencies had a different behavior subtly than what we see in the Sun. A first indication of what we call mixed modes, and I'll get back to that later because that has become very important in astroseismology. Another star that was observed quite early is one of our nearest neighbors, Alpha Centauri A, a star very similar to the Sun, slightly more massive, slightly older, and again showing the same kind of frequency pattern, which we could then use to determine quite accurately the properties of the star and test the internal features of the star. But all these observations were obtained using very large telescopes. We used, my group used one of the VLT telescopes, 8-meter telescopes, to observe Alpha Centauri A. So using an 8-meter telescope to observe one of the brightest stars in the sky is not something you do every day. So we needed additional observing facilities. And that came with the launch of these two satellites, the Kourou satellite, a French ESA collaboration, and the Kepler satellite launched by NASA. And these satellites have produced absolutely amazing data on stellar oscillations. And they have allowed us to study doing astroseismology all through the Hertzsprung-Russell diagram. These blobs mark schematically where we have stars that show oscillations. We have the solar-like stars, we have giants, we have hotter stars, we have white dwarfs. And in all these cases, we've obtained data, both from the ground, but to a very large extent from these space missions that have allowed us to begin to study how stars evolve throughout all their evolutionary phases. So an early result from Kourou, which has become very important, was the detection of solar-like oscillations in red giant stars. So this, by an analysis done by Joris de Ritter from Belgium. So what you see here are, again, these power spectra. The frequencies go from 75 microhertz here, down all the way to about 10 microhertz for the maximum power in this star. And so what you see here is the same pattern of oscillations. So we have the ability to obtain the observations, the information from that pattern. But of course, with frequencies that decrease as the stars are bigger and bigger. So we have this whole range of possibilities of observing these oscillations and thereby characterizing these red giants, certainly in terms of their mass and radii. And that has become very important in studying the galactic structure. Another area where the observations have been very important is in characterizing stars that are host to exoplanets. So Kepler was really built to search for exoplanets using the transit technique, where you look for the slight decrease in the luminosity of the star as a planet passes in front of the star. And the dip in light corresponds to the area covered by the planet compared with the total size of the stellar disk. So to use that to obtain the radius of the star, you need the radius of the planet, you need to know the radius of the star. And as I mentioned, we can actually, from astroseismology, determine stellar radii with an accuracy that's much higher than classical techniques. And so and we can also determine the stellar mass, which is required to infer the planetary properties when you find the planets using the Doppler shift of the star, the reflex motion of the star. So these data have been very, very important in characterizing exoplanet properties. But the other thing we can do, as I mentioned already, observing stars, observing the Sun as a star, we see these low-degree modes that penetrate all the way to the core. These are the modes that we see in other stars, and therefore we are able to determine ages of these stars that host the exoplanets. And that has allowed us to determine ages for at least a few handfuls of stars that are host to exoplanets. This was work led by Victor Silva Aguirre in Aarhus. And what we see here are examples of stars, both determination of stellar radii, but in particular we see a whole range of ages of these exoplanet hosting stars. Quite a few here around 6 gigayears, but also stars as old as 10 or 11 gigayears. And so these must be stars that are in a very early generation of Milky Way stars. So we see planets for this whole range of ages. And you might wonder how the exoplanet systems and possible life on these exoplanets has evolved in this time span, going from the age of the Sun, around 4.5 gigayears, up to 10, 11, 12 gigayears. So that is exciting, but the red giants turned out to be much more exciting than I had expected, or most of us had expected, actually, I think. And the reason is that we see these mixed modes. So this is a cutout of the schematic model of a red giant star. And we have the acoustic modes in the outer layers of the star, just like in the Sun. But then we have modes that are dominated by internal gravity waves in the core of the star. And remind you that the structure of a red giant is a huge outer convection zone, and then a very small helium core where hydrogen has been used up, and then outside the core a thin shell where hydrogen is still fusing into helium. and so by having these modes, these mixed modes, we actually get a possibility of studying the internal structure of these red giant stars. and this was first shown by a graduate student of Conny's, Paul Beck, who again looked, and you must be very tired of Howard spectra by now, but these are really the tools of the trade. That's where we get all our information about these stellar interiors. And what we see here is something that superficially looks like what we see in the Sun, peaks of power with a spacing that we can measure and determine the mass and radius of the star from that. But if we look more carefully, we see that there are intermediate forests of peaks. Here in the Sun, we will see just one peak. In this star, we see 3. Here we see also 3. Here we see 3 peaks. So we see these additional peaks, and that is a reflection of this gravity wave structure of the oscillations in the deep interior of the star. And we can measure then the spacing between these peaks. And then we also see, and that's something I didn't discuss in the solar case, we see this hyperfine structure if we blow up this part of the power spectrum. So we have this group of 3 peaks here. But each of these peaks are split again, and that splitting is caused by the rotation of the star. So we also get a way to measure the internal rotation of these stars, not in detail as we did in the Sun, but as it turns out, mainly in the core of these stars. And if we do that for a very large number of stars, in work done by Benoit Moser in Paris, we can make plots of the stars in a diagram where the horizontal axis is this acoustic mode frequency spacing that we also used in the solar case, and the vertical axis is this gravity mode signature that I pointed out in the power spectrum. And what we see is the effect of the evolution of the star. The frequency spacing becomes smaller and smaller as the star evolves up the red giant branch. very well defined in this case. And then we have a separate group of stars here with sort of intermediate to low acoustic frequency separation. And these are the stars, it turns out, where helium has been ignited in the core of the star. So superficially, if all we have are the surface observations, these two stars would look almost exactly the same. But of course, here we can very, very clearly separate them, and then we can begin to study the detailed properties of these internal region. Very small compared with the size of the star, not very much bigger than the Earth, but we have detailed information about the properties of this deep interior of the star. And then also we can look at rotation, and again, in this case, rotation for a group of stars is plotted against the stellar radius in units of the solar radius. So we go from stars that are on the subgiant branch, just a factor of 2 bigger than the Sun, evolving towards the red giant branch, and then a group of stars on the red giant branch, again with a helium core and hydrogen shell burning. And then a separate group of stars where we also have helium ignited and burning to carbon in the helium core. So what we see is a jump in rotation, and this what is plotted here is a rotation frequency of the core of the star in nanohertz. Just for comparison, the solar rotation rate is about 400 nanohertz. So we see that the core of the star is rotating somewhat more rapidly than the Sun, but far less rapidly than our models predict. And in the modeling, what we have to take into account is the fact that the cores of these stars contract as hydrogen is used up. And then, of course, if you conserve angular momentum, you would expect the core to spin up. And they actually spin up to very high rotation rates, maybe a factor of 100 bigger than what we see here. So what we have to infer is that there must be some mechanism for transporting angular momentum out of the core, and we haven't yet identified what that mechanism is. So this is one of the mysteries that we are now working on. Of course, you can always take magnetic fields, and that may be right, but we don't have any good models of how the magnetic fields would behave in the core of these stars. So here I have talked about mainly cool and low mass stars. And now we move on to hot stars and to Conny Aerts. And as I like to say, Conny likes it hot. So let's move to a short presentation from Conny.
Dear participants of the IAU in Busan, thank you for giving the opportunity for us Kavli laureates in astrophysics to present our work, even though it's only virtually in my case. So I'm very grateful to Jørgen for representing us over there with you. Now, it is really a great honor to have been selected as so-called representative of the second generation of astroseismologists in my case. So while Roger and Jørgen have worked on the Sun and on stars of low mass, cool stars, like our own Sun and red giants, I have been focusing throughout my career on more massive stars. So these are hotter stars, and some of them will later explode as supernova. Now, the first results that we got on the rotation of these stars, because that's really a key ingredient for the evolution of such objects. First results came actually from extensive ground-based network campaigns back in 2003, where we could measure for the first time the rotation near the convective core of such stars. This is really a key ingredient of stellar evolution theory, and we managed to get that for a so-called beta Cephei variable. So these are stars with masses above roughly 8 times the mass of the Sun. Now, as soon as we got fantastic data from the space missions, we swapped from doing network campaigns on the ground to the space photometry. So that was about 10 years after we had found this first initial internal rotation rate of this beta Cephei variable. And then I swapped to what are my pet modes. I mean by that gravity modes in fast rotators. So these fast rotators are stars of intermediate mass where we have gravito-inertial modes. So these are gravity modes that are highly affected by the Coriolis acceleration. And on the one hand, that gives a serious complication in the mathematical treatment of these oscillations. But on the other hand, the reward that you get is that you can measure the internal rotation profiles of such stars thanks to these modes. And we could only start doing that as soon as we had the 4 years of uninterrupted Kepler photometry. Now, meanwhile, we have hundreds and hundreds of such intermediate mass pulsators for which we could deduce the near-core rotation rate. And that by itself is important because the rotation in these stars really guide their chemical mixing in the envelope. And this is really what sets the life of these stars and what we need to age date them properly. So we are now in a fantastic time because we keep on assembling results for more and more of such stars, such that we can finally calibrate the theory of stellar structure and evolution for intermediate and high mass stars. I will let Jørgen explain you a little bit more about that, and I wish you a great continuation of this conference. Bye.
So let me just go back to what Conny mentioned here. Her very heroic observations for 21 years of a single star to try to obtain the oscillation frequencies of just these 6 modes. So again, here we have frequency, now we're talking cycles per day. But just from these 6 oscillation observed frequencies and modeling them with stellar evolution, she and her collaborators were able to obtain just more or less 2 measurements of the internal rotation of the star. This is a 9.2 solar mass star, a B star. And they could get a measurement of rotation in the deep interior of the star at a point, a frequency of 0.02 cycles per day. And then the rotation rate near the surface at a frequency of about 0.01 cycles per day. And say they could show for the first time a gradient in rotation between the core of the star and the surface. And this, of course, was, it's a very boring plot, but it's a very important result because the evolution of rotation plays a very large role for the evolution of the star. But then we can contrast that with what we now have with the Kepler data, the 4 years of continuous data. This is a 3.1 solar mass star, where rather than the 6 frequencies that Conny got from 20 years of observations, we have about 300 frequencies identified in this star. And so that's an extremely rich data set to study the internal properties of these stars. Of course, we need more data. Kepler has stopped operating. We're still far from done with analyzing the Kepler data. But we now have another mission launched in 2018, TESS, a mission again by NASA and the MIT. And TESS has a different observing schedule. It observes the whole sky for shorter periods, but it gives us a bigger sample of stars to analyze. And these massive stars are fairly rare. So having a broader range of the sky to study is very important. And the TESS data are now, of course, being analyzed in great detail. So one result that Conny collected based on data from very many different observations was again a measure of the core rotation of the stars as a function of the surface gravity. So going from main sequence stars with gravity log G of around 4 to 4.5, subgiant stars, and then red giant stars and helium-burning clump stars. And so here we see the same kind of effect, but for many more stars than I showed earlier. Again, the clump stars have a rotation rate reduced from the red giant. And now our task is to try to understand that from our stellar models. And this is very much an ongoing effort. But to return to these hotter and more massive stars, the physics of the stellar interior is more complicated than in the case of the Sun. These hotter stars on the main sequence have a convective core, which is then fully mixed. But outside the convective core, we expect that there's some penetration, some overshooting, causing additional mixing. Of course, in the core, we have nuclear burning, so changing the composition in that way. And then in the outer layers of the star, there could be atomic molecular diffusion. There could be settling, heavier elements sinking towards the interior, but also levitation, heavier elements being pushed towards the surface by radiation. And then, because, as Conny said, these stars are rapidly rotating, motion is set up in the interior of the star that might also cause additional mixing. There could be waves generated by the convective core that also transports both material and angular momentum. And then, of course, we also always have to worry about magnetism or be delighted by it as an additional challenge in our understanding the properties of these stars. So an analysis of stars like that was carried out by Mdi Pedersen, one of Conny's PhD students. And I'm quite proud to say that Mdi got her first education in Aarhus. And what she did was to look at models characterized by the mixing processes in the stellar interior. So as a function of the position inside the star, we have the convective core that's very efficiently mixed. Then we may have this region of overshoot outside the core. And then we have mixing processes, in this case modeled by circulation, induced by rotation, in the outer parts of the star. And so she could parameterize these three mixing processes and then try to fit models of the stars to the observations. And doing that, she obtained some very interesting results of relations between different properties of the star. Here indicated partly in color. So in this case, it's a central hydrogen abundance, which is a measure of age relative to the initial hydrogen abundance, so going from the very young stars to stars at the age of the main sequence. And then showing the relation between the mass of the convective core and the radius of the convective core. But also then showing here the radius of the convective core as a function of the age in units of the central hydrogen abundance, showing how the core shrinks with age, and again how that depends on the rotation rate in of the star, which then affects the mixing in the envelope. And then here the inferred envelope mixing as a function of the rotation rate, and you see a very strong correlation between the envelope rotation and the mixing processes in the envelope, really confirming that rotation dominates these mixing processes. So by studies like that and many other properties of stellar interiors, we can begin to benchmark our models of these stars and try to improve them. And I should mention, Conny didn't make that quite explicit, that what happens in this main sequence phase of the evolution determines the size of the helium core after the main sequence, and that has a very strong effect on how the stars evolve into the late stellar evolution phases, and finally how they explode as supernova. So to understand these late evolution stages, and of course how these create elements in the universe, we really have to understand these early evolution phases much better, and this is what data like that really are helping us to do. So Conny mentioned the fact that these stars are rapidly rotating, and to some extent that can be studied just in terms of modifications to the properties of the oscillations. We get oscillations that are not purely gravity waves. They are affected by rotation, become what we call gravity inertial waves. And Conny has been and her group have been very important in developing techniques to analyze these waves and use them for astroseismic inferences. But of course, as we increase rotation rates even further, we move from stars that are approximately spherical to stars that become oblates. And then we get an even more complicated oscillation spectrum and an even harder modeling effort. And so this is really the frontier for the study of these massive stars, something that Conny and her group collaborators around the world are working very hard on. And of course, this is going to be one of the next breakthroughs to get a better understanding of how these stars evolve. And of course, we get up to stars like Mdi stars, which are rotating so rapidly that they're losing matter from their equator. So astroseismology is extending over a broader and broader range of stellar properties through these fantastic observations and also from this fantastic analysis. So that's where we're going here, and of course, as always, we need more data. And fortunately, the European Space Agency is working on a new mission to both observe exoplanets and to do astroseismology with data that are of a quality similar to Kepler's, but covering much larger areas of the sky and therefore giving a much broader selection of stars. So Kepler is adapted, it's going ahead, and the launch date is expected to be in around 2026. It's a little bit late for me, but of course I'm now a retired emeritus professor, but I really hope to be around also in 2026 and share the fun of analyzing the wonderful data that we are going to get from Plato. And let me just end by where I started, emphasizing that this is a prize given to 3 scientists, but really we have to regard this as a prize to the whole community of scientists and technicians who have made all these wonderful data and analysis possible. So with that, I'll thank you very much for your attention.
Thank you so much, Professor, for that beautiful story of a half-century of work trying to understand the interiors of the stars, a detective story that would have been unimaginable before
yes.
that. Absolutely brilliant work. If you have questions, please go to the mic in the center there, and I'm looking online to see if there's any question in the channel. So please, this is your opportunity to ask a true pioneer.
Yeah, that was a great talk. Wondering what the applicability of the Asteroseismology to highly pulsating stars might be, and if you could learn anything interesting from that.
So you ask about pre-main sequence stars, basically.
Yeah, presumably.
Yeah. There are some observations of, not the solar-like oscillations, but oscillations of a type called delta Scuti stars in pre-main sequence stars. So yes, it is possible. One of the difficulties is that the early stars tend to be very active. And in the case of solar-like oscillations, we are talking about oscillation amplitudes of the order of maybe a few parts per million. And so stellar activity would tend to drown the signal for that kind of stars. That, of course, doesn't stop us from trying, and it might be possible eventually to do that. But for these other stars, the delta Scuti stars, there should be a chance, at least in the late stages of star formation, to get some information about from astroseismology.
Thank you.
Yes, please come to the mic. Thank you.
Hi, thanks for the nice talk. I have a simple question. So far, how far stars can astroseismology reach? Like how far stars can we reach with astroseismological approach?
Well, the Kepler stars are within a few hundred parsecs, and typically we are looking at stars fairly close to the. So your question is how distant stars can we look at?
Yeah.
So on the main sequence, we're looking at stars in the solar neighborhood. But for red giants, because of course they're bright, we can actually make a global characterization of red giants in much of the Milky Way galaxy. And that's very important because what we do with astroseismology, by measuring the mass and the radius of the star, is to get the luminosity of the star, because we have the radius, we have the effective temperature. And so from that, and the measured luminosity, we can then get the distance to the red giant. And from the mass of a red giant, we can basically get the age, because the red giant phase is quite short. So we have the potential to measure ages and luminosities of a broad range of stars, and that's very important for studying the evolution of the galaxy, because we can combine the age and distance determination with determinations of the chemical compositions of the stars and the the motion of the stars in the galaxy. And this is being used, for instance, to see evidence for the Milky Way galaxy is following smaller galaxies, because we can see that these galaxies, the stars that we see, are older than and have a different composition from the stars that were created in the Milky Way galaxy. So this is a very rapidly developing field that we call galactic archaeology, which also then depends on the astroseismic results.
Thanks for the answer.
Yes, one more question. Please go to the mic.
Thank you for your talk. I have a question. When I see some paper about the ages derived from asteroseismology, usually the age uncertainty is less than 10%, as I remember, very small. Can you explain why is the reason?
Sorry, could you?
I mean, why usually the uncertainty of the ages from asteroseismology is very small, less than like just few percent?
Yeah, well, yes, they are. It depends on where you are in the Hertzsprung-Russell diagram. The classical way to determine ages is to compare with isochrones. But if you look at stars with masses less than the Sun, then the isochrones become very condensed. And so that the age determination becomes very inaccurate. And that's where astroseismology really wins. For more massive stars, it's more comparable. But I should also say that this technique, of course, has been calibrated against the Sun. We know the solar age very accurately, of course, from radioactive decay, and the age we get out from applying the seismic technique to the Sun agrees very well with the age that we have from the radioactive decay. So I think this is a way to get ages that are substantially more accurate for quite a large fraction of stars compared with the other techniques.
And there was one more question in the middle. Let's go ahead and end with that one.
It's really inspiring, Jørgen. Thank you. My question's about the astro-seismic scaling relations. So we've seen how the uncertainties in the mass and the radius has been steadily being beat down from 10-15% down to about 5% is the recent number that I've seen. My hope is that you can comment on that and then maybe give us some insight. What will it take to beat them down to 1%? Thank you.
Well, that's a question for a whole different talk, actually. But the scaling relations are very useful as a quick fix tool to determine stellar properties. And as you say, it works relatively well. There are two issues there that I did not go into detail. The one scaling relation is the one that I referred to, which is fairly well determined as the relation between the frequency spacing and the mean density of the star, and we understand the reason for that. The second scaling relation is a relation between the frequency of maximum power and basically the surface gravity of the star. And we have no idea why that works, but it does work. And it has been calibrated against stars where we know the properties by different means. But of course, there are uncertainties also observational, and one major uncertainty also in the large frequency separation are the effect of the outermost layers of the star on the oscillation frequencies. That's a region where our models don't work very well because of the effect of convection, and also both the effect of convection both on the model, the structure of the star, and on the oscillations. So that's something that we are working very hard to improve. And one key aspect in trying to do that is to use hydrodynamical simulations of the near-surface layers of the star, both to get a better model of the structure of the star, but we're also beginning to be able to use these simulations to study the interaction between the convection and the oscillations that are excited in the simulations. So I think there's hope for an improved understanding of that, and that is really what we need to pin down the properties of stars with even higher accuracy.
Let's congratulate and thank our laureate once more.
Thank you very much.